Hi, and thank you for joining me as we journey down the mole road of stoichiometry. Our concept in this video is dealing with two other types of percent. In a previous video, we did percent yield. This time we want to look at mixtures. That mixture could be a solution, an aqueous solution, or it could be a purity issue. Okay? Now, both of these, the words in bold, that's our link from to and from our stoichiometry reaction. So let's take a look at this one. We have silicon tetrafluoride is formed with hydrofluoric acid, nasty stuff by the way. What etching means the removal of. Okay, and we have, let's go ahead and put our information, because this is a little bit more complicated. They tell me in the question that we collected this gaseous SiF4. This is key, over water. Okay, that's an important concept. So what is done when a gas is collected over water is you have a water solution there and gas is going to bubble up. So you're going to have your gas coming up and it's going to bubble up. So what that means is that up here you're going to have the vapor pressure of your gas that you collected by displacing the water. Okay? But you will also have, because it's a closed container and there's water here, you're going to have some water vapor present. So we have to apply Dalton's law. So Dalton's law is one of the gas laws. I hope you've had gases by now, but if not, watch carefully. So this tells me that my temperature of silicon fluoride is 15.5 degrees Celsius. Now it gives me my pressure, and that's my total pressure. We've set this system up so it will equal the same pressure of our atmosphere. Okay, and then I have a volume of 3.382. Yes, 3.382. I changed that to liters automatically. You'll see why in a minute. And the question says, how many grams of pure SiO2 must we have? So look at the implication there. By asking me what the purity of this SiO2 is, that's implying that this 12-gram sample is an impure sample. Okay. Now, if I want to get to the mole road here, I have to use the ideal gas law, Pevnert, and then I'm going to go moles to moles, and then moles to mass. Okay. So I first have to do Pevnert. Okay. And then I can hop into the stoichiometry, and then we'll use this percent formula. Now, to do Pevnert, we have to do a few changes. For one, I've already done one automatically. I changed my volume, but we also have to change our temperature because we always need Kelvin. So this is 288.65 Kelvin. Okay. Now, this is my total pressure. To get my pressure of my gas, I have to take away my vapor pressure of water. That would be given to you in the context of the question. And at this temperature, it's 1.77. So if you see something collected over water, then take away the water, because my total pressure was equal to my gas that I'm after, in this case silicon fluoride, tetrafluoride, and my water. So when I solve that, I take away water. Over water, take away water. Now, if you plug this into Pevnert, I would get 100.15, that's kilopascals, a volume of 3.382. You must use liters in Pevnert. Moles, R for kilopascals is 8.314. My temperature in Kelvin is 288.65. And that gets me onto my mole road. So that gave me a value of 0.1316 moles. Okay, so now I've got to delete this a little bit. I need some more room. Okay. So now what we're going to do, now we can do our mole road. So we only have 2 steps this time. So I just calculated from PeveNerd that I have 1316 moles of my silicon tetrafluoride. I want to eliminate moles of silicon tetrafluoride, and I want moles of silicon dioxide. That's a 1-to-1 mole ratio. And now I've got to go moles to mass. Now, this is going to give me the grams of pure silicon dioxide that must have been present in this impure sample in order to get this many moles of my silicon tetrafluoride. So my molar mass is 60.08 to 1. So I have 7.907 grams of pure. If you've calculated in a stoichiometry, you're dealing with pure and theoretical. Okay? Now, honestly, most questions would give you a little scaffolding for this. They'd say part 1, calculate the moles of silicon fluoride formed. Part 2, calculate the grams of pure silicon dioxide. Part 3, calculate the percent purity. So to calculate that percent purity, let me clean this up a little bit. Okay, so we have our mass of our pure substance was 7.907. Our impure sample was 12.00 times 100 gives us 65.89% pure in that sample. Okay? Now, I want you to pay attention here. You might want to know why I used 4 sig figs when the temperature had 3. Well, remember your rules for addition. All right. I go to the fewest decimal places. That's my last, whoops, that's really messing me up there. My last uncertain in that, my last uncertain there. So I have to yield to the furthest uncertain to the left, and therefore I would have to round it to 4 sig figs. So be careful, because when you're going to and from Kelvin, you often change your number of sig figs. Okay, I'm hoping this helps you. Have a good evening.